Hello everyone, my name is Guo Wenxu, a PhD student from the University of Electronic Science and Technology of China. I'm very honored to share my work titled Secure and Verifiable Inference in Deep Neural Networks. I will introduce my work from the following aspects. First, I will describe some background knowledge of deep learning. Then, I will explain the technical details of a proposed scheme. Security and performance analysis will be described last. Finally, I will summarize the work. Deep learning has been used in all aspects of social life, such as face recognition, autopilot, and medical diagnosis. As shown in figure, deep neural networks usually consist of one input layers, one or more hidden layers, and one output layer. Each two adjacent layers are connected by a weight. We call the models parameters. Given the training sets x and y, training a neural network is to find the optimal parameters for accurately reflecting the relationship between x and y. After the deep neural networks converge to precise accuracy, it can be used for subsequent inference. In this paper, we focus on the model integrity and user privacy in the inference process. We know that to support automatic servers, many companies such as Google and Microsoft provide outsourced deep learning servers, using them as machine learning as a server. However, it also brings various security and privacy concerns. In particular, particularly in inference servers, customers are very concerned about the model integrity and the data privacy once outsourcing them to the cloud. To address this above problem, we propose SecureDL to protect model integrity and user privacy. As shown in figure, our SecureDL consists of two genetic entities, a user and a cloud server. To achieve automatic outsourcing prediction servers, the user first outsources its deep neural networks model to the server. Then, the server allocated the resources for this model and release the API interface for prediction. In the end, the user submits the query request and to the servers and receives the predicted results. However, the above-associated prediction servers also bring about several security and privacy issues. Specifically, once the user associates deep neural networks model to the servers, the malicious servers may tamper with the model parameters for certain benefits. On the other hand, it's possible that the server abuses the user model parameters and even exploits the prediction servers to collect the user sensitive data such as the query request and the predicted results. Therefore, the goal of our SecureDL is to provide secure and privacy-preserving prediction servers. The workflow of SecureDL is as follows. To realize privacy-preserving outsourced inference servers while guaranteeing the model integrity, we first design a general function approximation algorithm to transform nonlinear activation functions to low-degree polynomials. This will facilitate the generation of sensitive samples and the application of leveled homomorphic encryption, we call LHE, in general deep neural networks. Then, we generate genetic sensitive samples to verify the correctness of model parameters in the inference process. In the end, to protect the user privacy, LHE is used to provide privacy-preserving deep neural network inference. We know that the following homomorphic encryption is a potential solution to provide privacy-preserving inference. However, it's needed to huge computational overhead. To address the problem, we explore the leveled homomorphic encryption in our SecureDL to encrypt user private data. LHE is more efficient than FHE, but only supports limited addition and multiplication in the subtest. This shortcoming makes LHE impossible to calculate complex activation functions such as ReLU and SigMod. To combat that, we adopt a function simulation algorithm for convert nonlinear activation to polynomials. However, there are two challenges to be addressed. One is that given an error, can any function to be converted into polynomial? The other one is that how to find the optimal low-degree polynomial. We give a theorem to prove that it's possible to approximate any function with a low-degree polynomial. Then, based on the theorem, give an error bound and target low linear activation function, we first initialize the degree of polynomial to 1, and that is n equal to 1. Then we get the approximate polynomial based on the least square approximation algorithm. Lastly, we verify whether the difference between the target activation function and the approximate polynomial is less than the error bound. If so, the current polynomial is returned as the final low-degree polynomial. Otherwise, let n equal to n plus 1 continue to generate approximate polynomial and iteratively verify the above operation until we find a degree polynomial that meets the above constraint. It is quite above. The adversary can change the orange model by tampering with the parameters that's to launch data integrity and tag. To address this problem, our main idea is to generate a small set of test samples denoted as sensitive samples to check whether the adversary has changed the orange model. Specifically, we first generate a set of sensitive samples which are very sensitive to model parameter changes. Then, as shown figure, we submit this sensitive sample to the cloud and bin the corresponding outputs. By comparing the output under the outsourced model with the output of the orange model, the user can verify whether the outsourced model is intact or modified. To generate the sensitive samples, the orange model or local model defined as FWX, and we assume that the adversary compromises the outsourced model by modifying the character parameters W to W plus delta W. And then, by solving the optimization problem shown in figure, we can find the optimal sensitive samples. We have transformed the nonlinear activation function to polynomial and prepare the sensitive sample for multimodal verification. To protect the user privacy, we adopt levered homomorphic encryption to encrypt all user-related state, such as the model's parameters, user query request, and the inference results. As shown figure, the user first encrypts its well-trained model and outsources it to the cloud. Then the server allocates the resource for this model and release API for the inference servers. In the inference process, once the user submits its encrypted query request to the cloud, the server performs the preset operation of the outsourced model and return the corresponding encrypted inference result to the server. In this paper, we adopt BGV homomorphic encryption to implement all subtext inference, which is widely proved to be CPA secure. In this section, we evaluate the performance of SecureDL in terms of the inference accuracy, detection accuracy, and overhead. As described in Table 1, comply with the existing activation function. The approximate polynomial with 2 or 3 degrees are sufficient to achieve the expected accuracy. We can say that the model classification accuracy on the approximation polynomials is very close to that under the orange function. We evaluate the detection accuracy of the proposed scheme. We consider 4 various subtle integrity attacks in our experiment. As shown in the table, the result shows that our sensitive samples have excellent detection performance. Finally, we test the cost of SecureDL and compare it with the state-of-the-art approach, that is cryptolates and SecureML. As shown in Table 3, our SecureDL is significantly better than SecureML and the cryptolates. In this paper, we have proposed SecureDL, which can verify the integrity of DNN models outsourced to the cloud, while protecting user privacy in the inference process. In the future work, we tend to further improve the universality of the model and find a way to reduce the computation and the communication overhead of SecureDL. That's all. Thank you.